In our last section, we're talking generally about functions and relations. And in this section, direct variation, that's going to mean a specific relation between two variables, and that's the relation where the ratio of those two variables is going to be a constant. So actually kind of seen this before referred to in a different way, kind of thinking of like a linear relationship. It's going to work the same way. I'm just going to call that direct variation now. So if we want to determine this, again, if y varies directly with a second variable x, we're going to have to find out, again, away from just by using a table if that's true. And if we do find that it varies directly with x, we're also going to have what's called a constant of variation, where again, if I was to write the equation in several different ways, like y equals k times x or y over x equals k is going to be in that term that we're defining as that constant. So good way to find this is, again, just by using the exact same relationship they're asking from up there. I like to use this one, just y and x, divide those, find out if that relationship is constant. So if I'm just using the values from my table, this is a lot like when we see rise over run before. If I put the y over the x in each case, so 2 and 1 as a corresponding pair, 6 and 3 corresponding x's and y's, 8 and 4 corresponding pair of those two, we do get that all three of those would simplify to the same value, so that value would stay constant. And again, that's what we're going to find is our constant k is our constant of variation. And yeah, that means that we found a direct variationship. If I do also want to write that as a function rule, again, function rule is easiest to write as like an input and output for a function, like with our last section. So y equals 2x is like saying if I'm looking for y as an output, multiply the input by 2, and that's going to get your resulting, again, y value from the table. Trying that again with the next one, we can just find, again, first of all, if that is a direct variationship in the first place. And that's just like, again, rise over run, y's over x's, just like your slope formula, really. 8 over 2, and then 11 over 3. Although if you guys are good with your fractions, you might already notice first two fractions are going to be equivalent because we can just multiply top and bottom by 2. Not the same, though, if I look at something like 11 over 3. That's not going to be the same value as the first two relationships. 4 over 1, 8 over 2, 11 over 3 is not going to hold constant. So if I found that that ratio is not constant between y and x, we can just answer that, nope, it looks like y doesn't vary directly with x. So if I can spell doesn't correctly, y doesn't vary directly with x. Directly with x, there we go. That is, again, just saying that, again, if I was to graph this as a line, I'm not going to form that straight line because the first 2 points fit on the same line, but the last one doesn't. So I don't have that constant ratio between my variables. Next two are ones for you to try, but again, kind of the same as what we've already seen with the previous two. We just want to check, do I have a constant ratio? If I do, we have a direct variation. And if not, again, we're just not going to be able to write that with that same kind of function rule. With the first table, this actually, I think, does make a constant of variation, even if it's a negative pattern. It just means that, again, if I still found that difference, or sorry, not the difference, but the ratio of your y's and your x's, y over x in each case is going to come out to -7 if I was to simplify all of those fractions. So if we do find that that is my constant of variation, -7, I could write that again like we did in the previous question with that function rule, just by holding -7, almost like your slope. If I was to graph that as a line, just -7x. So y equals -7x, we got input, we got output, that's my function rule. Trying that again with the next table, I know I've covered up some of that table. Well, let's find out if that works with our direct variation from your notes. Don't think this does either. Kind of like with our question B from up above, just because, again, if I find that those fractions are not all equivalent, notice I can't like all simplify them down to get the same value that we did for the first and the third questions. If I can't all simplify them down in the same way, if they don't come out to the same decimal, if I'm trying to check this in my calculator, I get about like 2.5 for the first, like 2.3 repeating for the second. Third one I'm not even going to find, but we know it's not going to be the same decimal. Just like with our answer from up above, we know that y doesn't vary directly because, again, I didn't find that constant of variation. We don't have that same ratio throughout with those two variables. So like 2 for the first, -7 for that other question. We don't have a constant variation for that last one that we tried. So now if I want to determine this way, just by giving, this time not a table, but instead it looks like an equation to find out if y varies directly with x, my goal is kind of the same as what we did from before. Again, if I'm able to express this in a way that the ratio between my y and my x is constant, that again is going to express a direct variation. And again, that will also allow us to find that constant if I'm able to just get y and x on the other side. So this equation might seem kind of awkward because we're not used to doing this, but if I was to divide both sides by x here, again, usually our goal is to solve and isolate for a variable. Here we're basically trying to get into this form where y and x are being divided. But if I was to take that first step, I have 3y over x is now equal to 7. Not quite my final answer because I still have that 3 next to the y. So if I was to take one more step, I'll kind of just write it next to it, and to divide the 3 from both sides, I would end up with something like this, which again does just describe a direct relationship here, a direct variation, because we have y over x. It looks like this side just matches what we would have as what we call our constant of variation. So yes, it looks like we do have a direct variation, and because we found that the right-hand side simplified is just that single value, 7 over 3, even though it's a little bit awkward, would kind of stand in for like a slope in this kind of context. So 7 over 3 is our constant of variation because, again, that same kind of ratio is always going to hold true. So if I was to try this next question, again, we eventually wanted to get it in a form that looks like this, where y over x is going to be a ratio we can describe, and whatever is left on that right-hand side is going to be our constant. If I try the first step might be to just divide everything by 7, just because I want to make that a little simpler for me. But even if I was to divide everything by 7, my next step, if I was trying to, like, let's say divide by x, could divide by x on this term, but I would also have to do it on the term next to it. So I'm not really going to be able to find a way to express this in a way that I'm just going to have y and x on one side as a ratio and everything else on the other. So if I'm not able to write the equation that way, again, because I would have, even though this is like a line equation, this still has what we consider that kind of y-intercept, so almost like a constant that we're adding. If I'm adding that constant, we can just say that no, this is not going to be a direct variation, because again, I don't have that direct connection with just those two variables. So if I have y and x, if the 3 wasn't there, this might work. But since I have that plus 3, again, this is not exactly going to work as what we call a direct variation. So trying it for yourself on the other two, again, goal is still the same. If you're to isolate that in a way that we can write y over x as a ratio and just constant term on the right-hand side, that would be your constant of variation. So even though this one looks like we have addition on part C, that actually does work as a direct variation, because again, if I'm taking the steps to write my equation in a way that y over x is a ratio, I can take a step first. What I did is I subtracted 3y from both sides to start the question. I then divided by x, which again, kind of a weird step because we're not used to dividing by x. But if I want to get them to look this way, I need to make sure I can do that. And then my last step, kind of like what we did from up above, where I divided 3 from both sides, get that 3 on top to cancel. If I want to get that negative 3 to cancel, I can do the same thing here. So dividing both sides by negative 3, I actually do isolate and just get a constant. And that is, again, a constant for my ratio between those two variables. So we do have a direct variation, negative 5 over thirds being that constant. Trying that again with a question next to it. Might seem kind of awkward here, but yes, this works as well, just because all I have to do here is really divide by x. Again, kind of weird, we're not used to dividing by x, but it still works. If I divide x from x, that's why it canceled on the numerator of that right-hand side. And even if what I'm left with is a fraction, we had fraction on the last two anyway, fraction's still going to be a constant of variation because, again, I'm able to express the equation that way as just a ratio of my two variables, constant on the other side. That's the exact form I'm looking for. I'm looking for a direct variation. So we can also do this with a setup, kind of like a proportion that we might have seen. So again, kind of says proportion in this question itself, but this time we're kind of describing a direct variation. As soon as I give that information, we know that this is going to work as a ratio between those two. Again, if they didn't vary directly, then I can make that equation. But if I know they vary directly, and we know that when y is 9, x is negative 15, something we can do to make our proportions easier in every case, like this is a fraction that I can always simplify. I know that I can divide both of those parts by 3 for the numerator and the denominator and make that into a little bit easier ratio to understand with the next part of this question. Because then if I'm given a y to find, we're trying to find y in this other situation, we know that when x is negative 15 that y is 9, and if that, again, is varying directly, this ratio is going to hold true, so that when I'm setting up a proportion, again, a proportion is always an equation using those two fractions. We know that, again, if y over x was my description, we don't know what y is yet, but in this new scenario, we know that x is 21. And we also knew that when I simplified that first relationship, we know that they vary in a ratio with a constant of 3 to negative 5. Or you can also say like negative 3 to 5. As long as just one of those values is negative, you're going to get it. So here, if you remember how to solve a proportion, we need to make sure we can cross multiply, or again, called the cross products rule as well. So negative 5 times y, 21 times 3, I'm just going to kind of simplify that and just put 63. But yeah, again, all I did for that was I just multiplied those two together. And then if I was to take a step here, because again, we still want to find y by itself, that means I have to do one last thing to isolate and divide by that negative 5. So you could say your answer is a fraction, negative 63 over 5. I think most commonly, though, on this type of question for direct variation, they're going to give you that as a decimal instead. Both are going to be valid for my answer, but again, that means if x has changed value, your y is going to change value as well. So since x got a little bit larger, I guess, yeah, going from negative 15 to 21, that's going to change your y value as well. So they're going to vary directly using that same kind of constant. Trying that again with the next scenario, again, you just want to make sure you can set up and solve your proportion. The proportion that we found from the original situation, 15 over 3, reduces as a constant of 5 to 1. So if I keep that 5 to 1 relationship constant, and if x is now 12, that means I can solve that the same way using my proportion, cross multiply. In this case, y times 1 is also pretty easy for cross multiplication. So if I just multiply 5 times 12 to get 60, that's my new y value, again, when x was 12. So this works also with word problems, and we're going to solve them again pretty much the same way we just solved the last one. So if I know that commission varies directly with sales, so commission, if I spell that right, varies directly with sales, means we can kind of express that like a ratio, just like with any other direct variation. If I'm told that for $1,000 in sales on the bottom of my fraction, we know that the commission is $85. That means that just like in that last scenario, if I'm given a new value for sales, I should also be able to find that matching new value for commission, because they should keep that same relationship. So I'm going to define a variable. Let's say that let C equals like your commission. You can think of that as like dollars. But yeah, we need to define that. I don't want to use x in this case because, again, x is kind of like describing our direct variation. We want to be able to move that around. But yeah, C is what's missing. We haven't found that yet. We know in this new scenario that $2,300 is what I have in sales. And again, sticking with that original ratio, could simplify it if we'd like to, but I'm just going to keep that original one. We know that this is going to be my proportion that I can then cross multiply to solve for that missing commission. And when I say cross multiply, actually it's easy enough here. All I got to do is multiply by 2,300, because I know that if I'm just trying to isolate for C, only thing on that side is dividing by 2,300. So really this is more like just inverse operations. The opposite of dividing by 2,300 is multiplying by 2,300. So keeping that right-hand side the same, we know that if I multiply the top by 2,300, I found this on my calculator, multiplying that and then dividing by 1,000. That does come out to, I believe, 195.5. If we're answering this as a dollar amount, let's put that in our units. 195.50 is going to be our new commission. Again, if I more than double in sales, I should also more than double that commission if that relationship is going to hold true. So this also works with that calories example with grams beneath it. So again, if you'd like to try that one, quick setup for my proportion, but I'm going to see if I can get through this one and reveal my answer. I did reduce this proportion, or simplify that proportion rather. If I know that for every 200 calories, that's going to correspond to 50 grams, that means we can simplify that relationship to 4 calories for every gram. And again, if I know that there's 70 grams in this new example, and we're trying to find that matching number of calories, I can just set up that same kind of proportion. I'm cross-multiplying, or in this case, really just multiplying by 70. So 70 times 4 is where I get that new calories total from, if that relationship, again, holds true. So when I said this is like a linear relationship, it was not quite a linear relationship. As we've seen, we don't want to be adding any kind of constants, so we don't want to be changing our y-intercept. But if I'm to graph these, nice thing with a lot of these graphs, if I just substitute 0 for x as an input, I know I'm going to have 0 for y as an output. So we actually know both of these graphs are going to start at what we call the origin of this graphing system. And then again, it says to use a table, because before we know anything about rise over run, some of you guys probably use rise over run for this anyway, but let's say if I substitute a value, I'm going to substitute 5 as an easy value for x. Reason why is because if I multiply 5 times that fraction 2/5, 5 would just cancel with the 5 from the denominator and just leave me with 2 from the numerator. So just like, again, rise over run, I can go up to 1, 2, 3, 4, 5 that I'm counting over would bring me to that next value for x. And again, that's just 1, 2, 3, 4, 5. Yeah, I want to make sure I had that right. 1, 2, 3, 4, 5. Yep, 5, 2. And you could also keep that, again, backwards. Let's say if I went -5, we know that that's just going to be -2 as well for kind of the same reason. It's just going to cancel 1, 2, 3, 4, 5, 1, 2, and leave you with just the numerator. This time, if I know it's negative, I know that relationship's still going to hold true. So not a great line there. But yeah, just kind of estimating there'd be a line between those points. Yours is probably better. But let's see if that is still true with a negative. Again, if I was to substitute like +1, 1 times -4, I would have that point. Again, if I was to multiply a negative by a negative, I could get a positive that way as well. So if I was to graph 0, 0, 1, -4, 1, 2, 3, 4, just like with any other slope, it's going to go down as I move to the right as long as it's negative. This looks like a graph for my second situation. Again, trying to keep this brief, so I'll just go ahead and reveal the last two answers, but kind of the same process. We're just using the table. 0, 0 is going to be a nice point to find because that's going to work for any direct variation. But besides that, again, just like with our last question, pick 3 as an easy number to keep your values positive, or integers rather. And then same thing, we could also just consider this like a slope for my last graph.